probability lists and tables. Now, the examples we did before, the events were, the conditional probabilities were different from the original probabilities. So, for example, if we randomly pick two children from a Lego club, and 7 out of 10 have brown eyes, after we pick the first child, the probability of the first child having brown eyes will be 7 out of 10. But after we pick the first child, there's only 9 children left. If the first child has brown eyes, the probability of the second child having brown eyes is now 6 out of 9, which is different from 7 out of 10. So those were not independent events. But if the events are independent, sometimes it's easier to make a list rather than to make a tree. So in this section we'll be making a list, and I'll start out with, eventually get to two dice, or rolling a single die twice. But I'll start out with just one die here. But if you're rolling a pair of dice, or then the probability of let's say a 1 showing up on the first die is not going to affect what shows up on the second die. So those are independent events. But anyway, we'll start out with just one die, and then we'll get into two dice. So if the probability of a standard die has sides numbered 1 through 6. 1, 2, 3, 4, 5, 6. A probability that the number showing is at least 3. Well, you can just make a list of the numbers that are at least 3, 4, 5, or 6, and count them. There's 4 of them. So the probability of that the die is showing at least 3 is going to be 4 out of 6. The total number of sides is 6. It's 4 out of 6, which reduces to 2/3. In a similar manner, there are 3 odd numbers in size 1, 2, 3, 4, 5, 6. The numbers 1, 3, and 5 are odd. So the probability the number showing is odd is going to be 3 out of 6, which reduces to 1/2. Okay? Here we want to find the probability of L complement if we're given L. So L is event 1, 4, 5, or 6. What's left over, not included, would be 2 and 3. So L complement would be 2 and 3. Count the number of sides, and L complement, that's 2 divided by 6, which reduces to 1/3. If L is 1, 2, 3, 4, 5, what's left off is 6. So L complement is going to be 6. That's only one side out of 6. So the probability of L complement is going to be 1 out of 6. Okay, so that's one die. But now if you have two dice, now we have 2 dice here, and we want, for example, or a single die rolled twice. Now it gets a little bit more complicated. We can still make a list instead of a tree, but there's going to be a lot more possible outcomes. So if, for example, we want the probability of the total showing is 5 on 2 different dice, then there's a lot of possibilities we have to consider. So we'll make a list of the possible outcomes. So we could have a 1 and a 1. Just make a list of possible outcomes here. 1 and a 1, a 1 and a 2, 1 and a 3, 1 and a 4, 1 and a 5, 1 and a 6. Or we could have a 2 and a 1, 2 and a 2, 2, 3, 2, 4, 2, 5, 2, 6. A 3 and a 1, 3 and a 2, 3 and a 3, 3, 4, 3, 5, 3, 6. 4 and a 1, 4 and a 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So 1, 1 would be the first die is showing 1, the second die is showing 1. 1, 2 would be the first die is showing 1, the second die is showing 2, and so forth. So we want the ones that add up to 5. So 4 plus 1 is 5. 3 plus 2 is 5. 2 plus 3, 1 plus 4. So there's 4 of them all together. So these 36 outcomes are the sample space, by the way. So there's 4 out of the 36. So the probability of that the number showing as 5 is 4 out of 36, which reduces to 1 out of 9. And then the next one is the probability that the number showing is 8. It adds to 8. Number showing, the two numbers showing add to 8. So that would be a 6 plus 2, a 5 plus 3, 4 plus 4, 3 plus 5, 2 plus 6. So there's 5 of them. So the probability that the sum is 8 is going to be 5 out of 36. Next one, at most 3. That means 3 or less. So that's going to be 2 plus 1, 1 plus 2, 1 plus 1. So 2 plus 1 is 3. 1 plus 1 is at most 3. It's actually 2, but it's less than 3. 1 plus 2, so this is at most 3. That means 3 or less. So it's 3 out of 36, which reduces to 112. So at most 3. 3 out of 36 reduces to 112. And then at least 10. So that's 6 plus 4, 5 plus 5, 4 plus 6, and that means 10 or more. So 5 plus 6 would be more than 10. So this is at least 10. So there's 6 of them all together. So the probability of at least 10 would be 6 out of 36, which reduces to 1/6. Okay, and we could some of the questions in what assign define events as low. 1 or 2 would be a low roll. The die is showing 1 or 2. 3 or 4 would be medium. 5 or 6 would be high. 1, 3 or 5 would be odd. 2, 4, 6 would be even. The probability of 2 low results. Again, we can make a list of the 36 possible outcomes. A 1 and 1 would be they're both low. 1 and 2, they're both low. 2 and a 2, they're both low. 2 and a 1, they're both low. So there's 4 out of 36 are both low. So the probability of exactly 2 low results, 4 out of 36, which reduces to 1/9. Probability exactly 2 medium results. Well, 3 and a 3 is medium. 3 and a 4 are both medium. 4 and 3 are both medium. 4 and 4. So it's 4 out of 36. So that's a probability of exactly 2 mediums, 4 out of 36, which reduces to 1/9. Probability of at least 1 high result. So exactly 1 high, there's only going to be 4, right? 5, 5, 5, 6. I mean, exactly 2 highs, rather. Exactly 2 highs there'd be 4 of them. 5, 5, 5, 6, 6, 5, 5, and 6, 6. But they say at least 1 high. So you could have 1 high and 1 not high. You could have 1 high and 1 medium, or 1 high and 1 low. So that leaves a lot more possibilities. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18. There's 20 of them all together. So it's going to be the probability of 20 out of 36, which reduces to 5/9. Okay. Okay, so this one here, if you draw a single card, in a minute we'll be drawing two cards, just like we started with the one die and then we went to two dies. So we start out with one card from a deck of cards. The sample space would be the 52 cards and a standard deck of playing cards. We want the probability of the card is either a numbered card or a red card, and in parentheses I wrote both. We usually, when we say or, we mean the inclusive or, which includes both. So either a red card or a numbered card or both. So I circled the ones in green. I circled the ones that are either red or numbered on both. So we want all of the red cards, whether they're numbered or not. And for the black cards, we want only the ones that are numbered. So if you count these all together, there's 44 out of 52, which reduces to 11 out of 13. Okay, so let's go into a sample of two cards, and we're going to let R1 be the event that the first card is red or numbered, and from part A, R1, probability R1 is 11 out of 13, or 44 out of 52, which reduces 11 out of 13. R2 is the event the second card is red or numbered. Now, I'll initially do these sampling without replacement. And if we sample without replacement, that means that after the first card is chosen, now there's 52 cards left. There's originally 52, now there's only 51 cards left. If the first card was red or numbered, then there's only going to be 43 remaining of the 51 that are red or numbered. So the probability changes a little bit. It's not a big change. 44 out of 52 changes to 43 out of 51. So these are not independent events. For independent events, the probabilities will stay the same. If you flip a coin and it turns up heads on the first toss, that's not going to affect what the second toss. Just if the coin is evenly weighted, you still have the same chance of getting ahead on the second toss that you originally had on the first toss. But these are slightly dependent. There's a slight change in the probability. If you're drawing, this is called sampling without replacement. We without putting the first card back in the deck, we drew a second card. So the probability that that both cards are numbered. So this is the formula for conditional probability. The probability of R1 and R2 is the probability R1 times the conditional probability R2 if R1. So it's going to be 44 over 52 times 43 out of 51. We can reduce the first fractions. 11 out of 13 times 43 out of 51. Multiply the numerators and denominators. We get 473 out of 663. If we convert it to a decimal, it's approximately 0.7134. That's sampling without replacement. And typically, when you're doing a survey, or when you, let's say, public opinion survey, you're not going to ask the same person twice. If you're sampling without replacement, we're not going to pick the same card twice here. We're sampling without replacement. So technically, those the events when you're sampling from a larger population are slightly dependent. They're not entirely independent. If you sample with replacement, then the probabilities don't change. So if we draw a card, and either it fits our criterion or not, either it fits the R1 criterion or it doesn't. R1 is meant the first card is red or numbered. It has probability of 44 out of 52, which reduces 11 out of 13. R2 is the event the second card is red or numbered. Now, if we put the first card back into the deck, all 52 cards are still there, and so the probability of the second card being red or numbered is still the same. It's 11 out of 13. And if we multiply those together, 11 out of 13 times 11 out of 13, 121 out of 169, as a decimal of 0.7160. So so there's not a big difference. Without replacement, we got 7134. With replacement, 7160. And that's because our sample size is small compared to the population. We have a sample of 2 from a population of 52. And when the sample size is small compared to the population, there's not a big difference whether you sample with replacement or without replacement. There's a little bit of a difference there. But with sampling with replacement, the events R1 and R2 are completely independent. Without replacement, they were slightly dependent. There was a slight change in the probability. Okay, so that's that. Okay, so there's one more example here with lists. Okay, so 1,000 patients are each paired with a patient with similar age and clinical condition, so that there are 500 pairs. These 500 pairs represent the sample space, and one patient within each pair is given treatment A, the other treatment B, and the results are shown in the table. So the A cured, for the first row is the A cured row. So and the second row is the A not cured row. The first column is the B cured column. The second column is the B not cured column. So in the A cured row, we have 400 pairs. The patient getting treatment A was cured, and they're both cured actually, and both treatment patients getting both treatment were cured. In this second phase here, there are 30 pairs where patient A was cured but B was not. A total of 430 pairs. Patient getting treatment A was cured. In 20 pairs, patient getting treatment B was cured but A was not. Total of 420 pairs where a patient getting treatment B was cured. There's 50 pairs where neither patient was cured. So anyway, we can use this to compute probabilities. The probability of both patients are cured, well, that's 400 out of the total of 500. So 400 over 500 is 0.8. Probability exactly one patient is cured. Well, that would be either B is cured and A is not, or A is cured and B is not. So you'll have 30 plus the 20 over 500, which is 50 over 500, which is 0.1. Neither patient is cured. That's the 50 here, 50 out of 500, 0.1. Probability patient B is cured. That 420 is the total for patient B out of 500. 420 out of 500 is 0.84. Probability patient A is cured. The total for patient A was 430. 430 out of 500 is 0.86. Probability patient A is cured if exactly one is cured. Okay, so let's do that on a separate page. Okay, so probability of A if exactly one. What's the probability? The conditional probability is the probability A and exactly one divided by the probability of exactly one. Probability of A and exactly one. Well, there's 30 pairs where A was cured and B was not. So exactly one was cured means B was not cured. So it's 30 out of 500. And the probability that exactly 1 was cured, well, there's 20 plus 30. There was 20 pairs where B was cured and A was not, 30 where A was cured and B was not. So there's 20 plus 30 were cured, were exactly 1 were cured, plus 30 out of 500. And the 500s will cancel. And we have 20 plus 30 is 50. So it's 30 out of 50, which is 0.6. And then part G, probability of B, if exactly 1. It's going to be, there's 20 pairs where B was cured and A was not. So 20 out of 500. Well, actually, I'll write the words here. B and exactly 1 divided by probability of exactly 1. So it's going to be 20 out of 500 divided by 20 plus 30 out of 500. And the 500s will cancel. 20 plus 30 is 50. 20 out of 50, which is 0.4. Okay. Okay, so that concludes this presentation.